To understand how general relativity treats the flow of time, physicists often test boundaries by stripping away one dimension of space. We are going to look at a universe with exactly two spatial dimensions and one dimension of time, a 2 + 1 dimensional flat space. In 1991, J. Richard Gott discovered a mathematical solution within this framework that permits time travel. The setup requires only two infinitely long, perfectly straight cosmic strings, which we see here as point masses, moving past each other at velocities close to the speed of light. This animated diagram shows the geometry around these masses. A cosmic string cuts a wedge out of the surrounding spacetime. It removes a specific deficit angle from the two-dimensional plane and stitches the remaining edges together seamlessly. General relativity dictates that the spacetime across these stitched seams must be identified at identical moments in time. The left edge and the right edge are the exact same physical location, at the exact same clock reading. When a test particle navigates around the outside of these two rapidly approaching strings in the opposite direction of their travel, it exploits that timing rule. The particle's trajectory loops through the identified seams and intersects its own past. It completes a closed time-like curve. The mathematics of this solution are exact. The gott spacetime contains no singularities, requires no black hole event horizons, and obeys the weak energy condition, meaning it does not rely on hypothetical negative mass. The isolated math works. The physical question is whether a universe populated by slow, ordinary particles can ever naturally evolve into this specific extreme geometry. Physicists generally assume the laws of nature prevent the formation of closed time-like curves. Stephen Hawking formalized this assumption as the chronology protection conjecture. Researchers usually point to quantum fluctuations or highly localized energy conditions to explain how spacetime destroys a time machine before it can operate. Back in 1992, physicists Sean Carroll, Edward Farhi, and Alan Guth took a completely different approach to the gott spacetime. Instead of analyzing the local curvature or tidal forces near the collision, they abandoned the local spacetime picture entirely. They mapped the total momentum and energy of the universe into an abstract mathematical landscape, analyzing the limits of the entire system at once. In order to prove a physical machine cannot be built, they looked at the topological constraints of its pure parameter space. Their method relies on holonomy. In general relativity, spacetime curvature is measured by seeing how a vector transforms when dragged around a closed loop containing mass. This animation illustrates how that works in 2 + 1 dimensions. When the vector returns to its starting point after circling a mass, its angle is visibly rotated. That specific Lorentz transformation mathematically defines the exact energy and momentum of the enclosed particle. For standard particles moving slower than light, this is recorded as a matrix. We classify this specific type of matrix as time-like. Finding the total momentum of a multi-particle system requires multiplying their individual matrices together. You cannot simply add them up linearly, like you do in special relativity. This non-linear math creates an algebraic loophole. Multiplying two perfectly normal, time-like matrices representing ordinary matter can produce a mathematical output that is space-like. The total momentum of the system becomes tachyonic. The gott time machine relies precisely on this state. You need two massive particles whose combined momentum crosses into the tachyonic threshold. Matrix algebra alone allows ordinary matter to combine into a tachyonic system. The barrier to building a time machine is not found in momentum equations. To locate that barrier, Carroll, Farhi, and Guth turned those transformation matrices into physical coordinates. This diagram maps the parameter space of the Lorentz group. It forms a three-dimensional cylinder known as anti-de Sitter space. The top and bottom edges are mathematically linked, making the vertical time axis periodic. Every universe begins its evolution at the origin, the identity element in the lower left corner. Ordinary particles with time-like momentum travel along upward curving geodesics. You can trace these paths radiating outward from the origin and eventually refocusing halfway up the cylinder. The tachyonic matrix required for the gott time machine sits in a very specific location. It exists entirely inside this shaded wedge, isolated from the time-like paths. A direct, synthetarical path drawn from the origin can never reach this tachyonic zone. However, because the cylinder's time axis is periodic, you can mathematically draw paths that exit the top, loop through the bottom, and strike the wedge. If you strictly follow the boundaries of this standard cylinder, the topology implies you can reach the time machine state by combining enough momentum paths. But a physical universe does not periodically reset its mass to zero. The deficit angles cut by moving matter accumulate permanently. To accurately map this physical reality, the cyclical timeline must be removed by switching to the universal covering group. The geometry of the cylinder is sliced open and unrolled into a flat two-dimensional plane. The vertical time axis now stretches to infinity. The tachyonic wedges that allow for the Gott machine are permanently isolated in distinct, staggered pockets moving up the diagram. Next, we set the initial conditions. For a universe to be mathematically open, the total deficit angle removed from space must be less than 2 pi. That means our open universe must be located somewhere on this central axis, strictly confined between the 0 and 2 pi markers. To determine the absolute limits of where this universe can evolve, we project its future light cone upward. The outer edge of this light cone completely misses every single tachyonic wedge. An open universe simply lacks the geometric reach. No dynamically allowed combination of normal particles, undergoing any series of collisions or decays, can ever cross the void to achieve the specific momentum state required by the Gott time machine. This mathematical proof carries one important caveat. A closed universe has a much larger total deficit angle of exactly 4 pi. Starting higher on the vertical axis shifts the light cone. It points the boundary of possible evolution directly at a tachyonic wedge. A closed universe actually can dynamically evolve a Gott tachyon pair out of static, slowly moving matter. But physicist Gerard 't Hooft calculated the physical consequence of reaching that specific threshold. As the closed universe reaches the exact velocities needed to build the time machine, its spatial volume begins to collapse. The entire system collapses to a point with zero volume. The crunch destroys the universe well before any closed time-like curves have time to form. General relativity contains extreme theoretical loopholes, but whether you trace the local mass of a closed space to its collapse or map an open universe onto an infinite topological plane, the underlying architecture rigidly enforces the flow of time.